Now after the link has been established and a test tone is heard at the receiver, now we will try to perform the experiment wherein we want to measure the carrier to noise ratio. Now we have switched on all the carrier, the transmitter is off, the satellite emulator is off, and right now the receiver is receiving at 2.4 gigahertz and it is showing a noise floor of 17.0 dB microvolt. So that means this is the noise floor of the receiver and it cannot receive below this level. So this is the noise floor in dB microvolt, 17 dB microvolt. Now we will switch on the transmitter and the satellite. Now as in uplink, the uplink is at 5.74 gigahertz and downlink is at 2.4 gigahertz. So switching on the satellite, the receiver starts receiving the signal. Now as you can see, it is reading around 83.5 dB microvolt. So 83.5 minus 17 is the carrier to noise ratio of receiver with a carrier level transmitted from the satellite. Now this carrier to noise ratio can be varied by using this path loss or attenuator. Now if I change the path loss, you will see that because the receiver is saturated, so with the pot turned almost halfway, there is no change in reading, but because this path loss has an attenuation of 40 dB, so we now start receiving a very low signal. Now right now it is reading around 27 dB microvolt. So 27 minus 17, this is the carrier to noise ratio at this instance when the path loss pot has been turned fully anti-clockwise. So depending upon the carrier level, the noise floor will not change because that is the limit of the receiver, and with the change in carrier level, the carrier to noise ratio will change. So in order to achieve a very good carrier to noise ratio, either the noise floor of the receiver has to be brought down, which is an expensive process, or a carrier level can be increased by using high gain antennas. Now we can also measure the signal to noise ratio. Now for measuring signal to noise ratio, we have to first establish a link at a particular carrier to noise ratio. So now we will try not to feed any signal. So we will, at the transmitter end, we will not put any baseband signals. Now we will use this scope and try to measure the noise floor of the receiver at say video input. So now we have connected at the video output, and first this is selected at, this is the DC coupled. Now while measuring signal to noise ratio, we have to ensure that the carrier is on. We can check this by the test tone, and now as you can see, the this is reading a peak to peak level of around 150 millivolts. So this is the noise figure of the video amplifier used at the receiver end at the baseband output. And now we try to feed some signal at the transmitter baseband input. We can keep it AC coupled also. Now as you can see, this peak to peak is reading around 2 volt or 2000 millivolts. So 2000 millivolt is the peak to peak signal which has 170 millivolts of or 150 millivolt of noise already embedded in it. So the actual signal level is 2000 minus 150, that is 1850 millivolts. So 1850 divided by 150 will be the signal to noise ratio in numerals, and one can convert it into dB using the formula given in the manual. So this is how we can measure the signal to noise ratio at the receiver end of the satellite link.